In this video, we're going to talk about systems of equations. A system of equation is a set of equations. And a solution satisfies all of the equations in that set. Now, a system or a set of equations may include two equations or more, 3, 4, 5, okay. Also, those equations may be of a certain type. We're going to look specifically at two linear equations when we look at this material, but you could apply these same strategies to three equations, three variables, and they could be linear or they may not be linear. They could be quadratic, right? So these equations are going to represent lines, but you could have equations that represent parabolas or any other shape. Okay. So for two linear equations specifically, there are three possible solutions that we could get. Since we're dealing with two lines, there are three possible ways that two lines could interact. The first, I think, is the most obvious, and that is that our two lines might intersect. So we could have intersecting lines. And so maybe we have two lines that cross each other at some point. And the point where they cross is the solution. So the intersection point, this guy right here, do this, would be the solution. Since the solution is a point, the answers for these are going to have both an x value and a y value. Okay, the other possibilities, maybe our lines do not intersect. Maybe they're parallel lines. So we know a little bit about parallel lines at this point. We know that they have the same slope. And because they are slanted in the same way, they can be a fixed distance apart and never touch. So in that case, we don't have any intersection points to pinpoint. So in this case, there is no solution. There's no points that would satisfy both equations. Each line here represents an equation. Okay, and then the third possibility is that we may have two different equations, but when we go to graph them, they actually graph to be the same line. I call those overlapping lines. So maybe we have a solid line and a dotted line, and they are overlapping. So if two lines overlap, then they have infinitely many points in common, right? All the points on this line they share because they're essentially the same line. Now I like to point out that although there are infinitely many points on this line, this is not all real numbers or all points in all of two-dimensional space, right? We are restricted to points only on this line, but there just happens to be infinitely many of them. Okay, so in this case, we'll just say that we have infinitely many solutions. Now there is some terminology that goes along with these last two possibilities. So we usually say if the, I'm going to think for a second here. Okay, so if the system has a solution, notice we had a solution here when they intersect and here when they overlap. We would say it's a consistent system. But if the system does not have a solution, we would say it's inconsistent. So sometimes we say for parallel lines, this is an inconsistent system. Okay, and then the other terminology you might see, if the lines that we draw for each equation, if they are separate lines, like these first two scenarios, then we say that the equations are independent. Each equation represents a different line. But if the two equations happen to represent the same line, we say that they are dependent. So we would say that for the overlapping lines, we have dependent equations. So you may see the words inconsistent or the word dependent as you're working problems either online or in the textbook, and that's what those words are referring to. Okay, so let's take a few minutes to look at how to solve a system of equations now that we know what the possible solutions are. There's three methods that we could use to solve. We could graph the two lines and look for the place where they touch. Or we can use some pencil and paper methods where we use substitution or something called elimination. In this video, I'm not really going to address the graphing method. In my class, I usually give you a bunch of problems online so that you're able to use the graphing tool, because sometimes it's difficult to graph accurately on our own by hand, and it can be difficult to locate the solution without a lot of guidance. So the graphing tool online usually does the best job of showing you how that works. So I'm going to pay more attention to substitution and elimination. The substitution method looks this way. This is just sort of a summary. Usually you guys come in knowing a lot about both substitution and elimination, so I just want to remind you of the details if you've forgotten, or if it's been a while, just kind of give you another overview. Okay, so the substitution method, basically the idea is we're going to have our two equations, like we mentioned earlier. We're going to pick one variable from one of the equations and isolate it or get it by itself. And then we're going to substitute for that variable into the second equation. Because we want a solution that's in common between both equations, we want to make sure we use both equations. So when I substitute, I have to make sure I substitute into the equation I have not used yet. I don't want to go back to the first equation, or I will sort of be working in a circle. Okay, so here's number 22, I guess, from your book. We have two equations, 3x plus 5y equals 2, and 2x minus y equals negative 3. So we want to choose a variable to solve for or isolate. And in general, the substitution method is going to be a lot easier if you have a variable that doesn't have a coefficient, which we have one right here, I think you can spot. So that's the variable I'm going to solve for. So I'm going to solve for y. Let's label these equation number 1 and equation number 2. I'm going to solve for y in equation number 2. So I'm starting with this. I want to get y by itself, so I'm going to subtract my 2x to the other side. And then I don't want negative y, I just want regular y. This negative here is really like a negative 1, it's sort of implied. So I'm going to divide everything by negative 1. When I do that on both sides, on the left side the negative 1 goes away. On the right side, both parts get divided by negative 1. So this changes all the signs. This becomes a positive 2x and a positive 3. Okay, so I've done that first part. I've isolated y in the second equation. Now I want to substitute for y in the first equation. So here's my first equation. Anywhere where there's a y, instead of y, I'm going to put in 2x plus 3. So I'm going to substitute for y in equation number 1. So I have 3x plus 5, but I'm not going to put in a y, I'm going to substitute in a 2x plus 3 equals 2. Now the whole idea, the whole point behind substitution is if we have two variables, we can't solve for both variables at the same time. So we need a way to solve for them one at a time. Substitution is one option, right? By substituting for y, now I have something that has only x's in there, and this is something I'm familiar with. I can solve this, right? So I think the first step here, I think you can figure that out, is to distribute our 5. We need to get rid of the parentheses first. And then we can combine like terms. Maybe at the same time we can move this 15 over to the other side by subtracting. So I'm going to get 13x on the left equals negative 13 on the right. And if I divide by 13, looks like x is negative 1. Okay, and if you go back to the very beginning, remember we said that in this case the lines are overlapping. Not overlapping, intersecting. Alright, so the place where they intersect, the x value is at negative 1, but it's a point, so we need both an x value and a y value. So I want to go back and solve for y. That'd be the third step I do here. I'm just going to put it right down here. You can solve for y in various ways. In the case of substitution, because we've already isolated y, this is a really easy place to find the other variable, which in this case is y. But you could also use either of the original equations, because this is a common solution. It doesn't matter which one you use. We should get the same y value for all possible equations. Okay, I'm going to use this one because I think it's the most direct route. So I'm going to put in x to be negative 1. Looks like we get y is 1. So our final answer, our solution, will be the point negative 1, comma 1. Okay, so I hope that gives you a good idea of what substitution looks like. Right? We isolate one variable, substitute for that variable in the second equation. And then remember, our solution is going to look like a point because these are intersecting lines. Alright, let me show you another example. This time let's talk a little bit about the elimination method. So the elimination method is a little bit hard to describe in words. But the basic idea is that we want to eliminate a variable, and that will again allow us to solve for the variables one at a time. So to eliminate a variable, we would like the coefficients, the numbers in front of that variable, to be opposite. So for example, if I want to eliminate x, I would like to get the x's to be maybe positive 5x and negative 5x. And so the next step kind of addresses how to set that up. So to get them to be, the coefficients, to be equal and opposite, we're going to multiply one or both equations by a number. So we're going to do some setup and get the coefficients to be opposite. And then we can either add or subtract the equations to eliminate a variable. In general, I like to add because I think that causes less confusion, but in reality you could do either one, whichever one suits your situation, or really whatever is your preference. Okay, so here's number 39. We have two equations, 2x plus 3y equals 5, and 4x plus 7y equals 11. Which variable looks the simplest to eliminate? If we look at the coefficients for y and x, right, the coefficients for x are close in the sense that we could very easily multiply the top equation by 2 and get these to both be equal and opposite, or negative 2, I guess. Okay, so again, let's label these equation number 1 and equation number 2. So to set up our coefficients, we're going to multiply equation number 1 by, I want to do -2 because I'd like for this to be a negative 4x and a positive 4x so that when I add them together, they go to 0 and the x's are eliminated. Okay, so I probably should have written above that here that we are eliminating x, right? And you could have chosen to eliminate y. The problem would have looked a little bit different, but really not much. Okay, and we'll definitely get the same answer whatever route we choose, as long as we operate correctly. I did not spell that right. Okay, so we're gonna move on and multiply equation number 1 by -2. And I need, even though I'm focused on the x's, I need to multiply the whole equation by -2, not just the x value. So I'm going to end up with -4x minus 6y equals -10. I want to multiply the whole equation because I don't really want to change the way the equation is set up. I just want to change the way it looks, right? This equation, by multiplying everything, it still represents the same line. It doesn't really change anything. Okay, and then I didn't really need to do anything to equation number 2, so I'm just going to copy that one down underneath my new equation number 1. And now that I've got it set up the way I want it, the coefficients are opposite, I'm going to add those two equations together. So the -4 and +4, 0x, or really this is just 0, you can even leave it off. -6 and +7 would be +1y, and -10 and +11 would be +1. So really, if I boil this down, I have y equals 1. And for this one, I don't have to even do any solving. Okay, so just by eliminating x, I was able to get the value for y. Same thing is true for this example. The solution is a point, so now I want to take this y value and go back and find an x value to go with it. The same thing's true for this problem. Because it's a common solution, it's going to have the same x value whether I use equation number 1 or equation number 2. I don't have that handy place that I had for substitution. It just doesn't work the same for elimination. So I have to use one of these two original equations. Okay, so now I'm going to solve for x. I'm going to use number 1, not for any good reason. Either one, like I said, will give you the same result. So I'm going to substitute y to be 1 in equation number 1. So I'll have 2x plus 3 times 1 equals 5. And so really 3 times 1, that's 3. So I'm going to subtract 3 over. And if I divide both sides by 2, looks like x is +1. So my solution is the point 1, 1. Okay, we didn't draw the graph for these, but again, if we were to draw the graph for both of these equations, we would see that these lines intersect, and the place where they intersect is the point 1, 1. Okay, so both of these examples that we've done so far, just to kind of show you both methods, have been the intersecting line type. Let me give you an example where it's not an intersecting line type, so you can see what that would look like. So I have that here somewhere. Here it is. Okay, so here's an example. Again, we have two equations. I'm going to label them 1 and 2. We have 2x minus 4y equals 4, and we have -3x plus 6y equals -6. Okay, let's solve this with elimination. We could eliminate either variable. Let's choose x again. So we're going to eliminate x, which means we would really like for the coefficients to be, if I'm going to add the equations, I want them to be equal and opposite. So what do I need to multiply equation number 1 by? 3. And what do I need to multiply equation number 2 by? 2. So if I do that, if I multiply equation number 1 by 3, I'll have 6x. If I multiply equation number 2 by, number 2 by 2, I'll have negative 6x. Okay, and keep in mind I need to multiply the whole equation. So for equation number 1 becomes 6x minus 12y equals 12. And if I multiply equation number 2, I'll have negative 6x plus 12y equals negative 12. Okay, now the focus has been on the x because that's the goal, the variable we're trying to eliminate. However, this is the point at which we sort of recognize, hey, something fishy's going on here. Okay, so when I add these up, 6x and negative 6x, that's 0x. Negative 12y and 12y, that's 0y. And 12 and negative 12, that's 0. Okay, so this phenomenon can happen either with elimination like we see here or with substitution. If your variables drop out, because these are multiplied by 0, essentially this whole side is 0. If your variables disappear, then you want to look at what's left. So if what you have left is a true statement like we have here, then that means that we have the case where these two lines would overlap. If we were to graph them, they would actually represent the same lines. So if it's true, we have infinitely many solutions. If I'm not going to work a separate example, but if we were to do this same process, or maybe we use substitution and the variables drop out and you get something like 0 equals 5, which is obviously false. Okay, if the statement you get is false, then that implies that you have parallel lines. You have lines that don't ever touch. They don't have any common solutions. So in that case, it would be no solution. Okay, so now sometimes this is not my personality, okay, but sometimes you can spot that at the very beginning. I'm kind of I know what to do, so I'm going to do my process, and that's not always the best. But if you can look at the equations you have before you get started, sometimes you can recognize that either they're multiples of each other, which would be the case where they overlap and there are infinitely many solutions, or you may notice that they're multiples of each other on one side but not on the other, and in that case that would represent the parallel lines, right? No solution. So these, I think, if you were to multiply by 1.5, right, you would get this equation. Same thing here, same thing here. So if you notice that at the very beginning, then maybe you would have saved yourself some time. Okay. But either way, now you know how to deal with that and you know what it looks like. Okay, let's take one more example before we finish. This is a word problem that makes use of systems of equations. So this one says a student takes out 2 loans totaling $5,000. Each loan is at a different interest rate, one at 4% and one at 6% annual interest. The total interest after 1 year is $254. Find the amount of each loan. Okay, so in a word problem, right, you want to set up some variables. And because we're dealing with systems of equations right now, we're going to use 2 variables to demonstrate that. So the question at the very bottom here, find the amount of each loan, that's what we want our variables to represent. So let's let X represent the loan at 4% interest. And let's let Y represent the amount of the loan at 6% interest. And this is how much money we're borrowing, right? Okay, and then if we're going to use 2 variables, we need 2 equations to solve. You could look at the two facts here. The first fact deals with the amount of money that you have, that you're borrowing. Okay, and it says that the student takes out 2 loans totaling $5,000. So if we total up our 2 loans, if we add them up, they should add up to $5,000. That's one equation. All right, and then the rest of the information in this problem deals with the interest. Remember, for interest, we're going to take the amount of the loan times the interest rate. And in this case, the time that we're working with is just 1 year. So we're multiplying by 1, although that's not going to show up. Okay, the amount of our loan is our variable. The interest rate is the 4% and 6%. So we're going to multiply those together to calculate the interest for each loan. And we're going to write the percentage as a decimal. So 4% would be 0.04 of the amount of this first loan. Okay, so 4% of X will give us the interest we earn. Wait a minute, it's a loan. The interest we owe. Okay, for the first loan. And then we're going to do the same thing for the second loan. 6%, for 2 places to the left, times the amount of the loan. This will calculate the interest we owe from the second loan. If we add that up, it says the total interest after 1 year, it should say the total interest owed, okay, would be $254. So that's the logic you can use to set up these problems. The setup for these is very often the hardest part. The rest is just based on those solving strategies we were just looking at. So you could use either method here, either substitution or elimination. Okay, for this time I'm going to use substitution. And I'm going to solve for y in equation number 1. Let's label these. And I think you could probably do that in your head. Basically, I'm just going to subtract x over to the other side. And then I'm going to substitute for y in my second equation. Okay, so I'll have 0.04x plus 0.06, but instead of y, I'm going to put in 5,000 minus x is equal to 254. And now, just like we mentioned earlier, I have all x's, so I can solve for x and sort of solve for the variables one at a time. Okay, so the first step in that process is to distribute. So 0.06 times 5,000. I think it's 300. Make sure you check me on that. And now we can combine our variables. We can move this 300 over to the other side. So 0.04 minus 0.06 will be a negative 0.02x. And 254 minus 300, I think negative 46. Okay, so if we divide by negative 0.02, it looks like x is going to come out to 2,300. And again, please check my math. I think that's right. Alright, if you go all the way back to the top, remember we said x was the loan at 4%. So this student is borrowing $2,300 at 4% interest. And the y, remember though, I'll write it down off to the side here. Remember the y is 5,000 minus x. So if I need to, you could probably do it in your head, but if you want to write it down, you could take 5,000, subtract the value for x. Okay, so it looks like Y is going to be 2,700, and this was the loan at 6%. Alright, so I hope that gives you a good idea of systems of equations.